start the session, or the first speaker is Gale.
Thank you. So I'm going to be talking about localization. I'm a fourth-year PhD student at the University of Queensland, and the localization problem isn't particularly well known, especially compared to things like the measurement problem. It's an issue particularly in relativistic quantum theory. There's a lot of misconceptions, and generally in the literature people get the same result over and over again, usually independently rediscovering things in effect. And so the purpose of this talk is to try and clarify a few of these, this background literature. I have a preprint out on the same name of this talk that goes into a lot of this in more detail, but here I will be presenting things a bit more motivated from the perspective of measurement. So before we begin, or as we begin, what is localization? Well, in non-relativistic quantum mechanics, localization is in fact a very straightforward thing. It's just a matter of talking about where things are. It's defining a position operator, let's say, or a number operator, or any number of observables that we might want to define. And we can just simply say, this is where our system is somewhere in space at some time. But things get a lot more difficult when we add in relativity. And then it becomes a question of, can we talk about where things are relativistically? And the answer to that is, it's complicated. In the most crudest form, the localization problem is that we honestly just do not understand how to talk about localization in relativistic quantum theory. And there's a number of ways to motivate localization. The reason why we should care about the localization in relativistic quantum theory. There's a recent paper by Chris and Uenaga who have looked at localization in the context of algebraic quantum field theory because they want to address this question of where measurements occur, when they occur in space-time. But localization also appears in other areas of relativistic, other areas of relativistic quantum theory. For example, in the context of quantum reference frames, where we take reference frame systems like rods and clocks, and we treat them as quantum mechanical systems, we want to know where these quantum systems are. Likewise, if we're working in gravitationally-induced entanglement, not just in the non-relativistic regime with the Newtonian approximation, but if we want to treat things relativistically, then we actually care about some mass here, some mass somewhere else, and as they induce some where they can induce some entanglement through gravity. But especially in the context of thank you. Especially in the context of quantum information, localization also is very relevant. And there's a very nice review article by Danny and Asher that goes into or covers aspects of localization pertinent to relativistic quantum information. There's a very nice quote I want to just quickly read out, at least in part, which is how localization pertains to measurement, but particularly how it pertains to aspects of detectors. And as they say, how can we manage to ensure that two detectors have zero probability of overlapping? There appears to be a fundamental trade-off between detector reliability and localizability. The bottom line is how to formulate a relativistic interaction between a detector and the detected system. This problem seems to be very far from a solution. Completely new notions have to be invented. And I absolutely agree with this conclusion, although I don't completely agree with this framing. And I'll try and articulate my own views towards the end of the talk. But also just to get to this, to clarify how we should even be thinking or talking about localization, because there are two different particular conceptions that you want to often find in the literature. When we're dealing with relativistic quantum theory, for instance, we often talk about things in a space-time, four-dimensional space-time way. We want to talk about some interaction, some coupling, some measurement as it occurs in some space-time volume. For instance, the Fischer formalism I put up at the start takes this kind of conception. But there's a contrasting perspective of where things can be found, of how things can be localized, which is a three-dimensional conception, where we fix some space-like hyperplane, and we can define some volume on that hyperplane where our system or observable lives, with the idea being that I know my system is in this volume, and that my system cannot be found anywhere outside this volume. Likewise, in the space-time four-dimensional case. And this will lead to two competing notions of localization, which will have mutually exclusive properties, as we'll see. Now, I want to focus on this three-dimensional conception of localization first, which is associated to something called the Newton-Wigner localization scheme. The Newton-Wigner localization scheme was developed all the way back in the 1950s, where they took this axiomatic approach to try and talk about where things are, to try and define a localized state. And the axioms that they came up with were, first, linearity. That is, if I put my localized state in a superposition, it will still remain localized. That might seem a little bit peculiar, but what's going on is that we have some epistemic uncertainty, maybe, of where our state is localized, but we ultimately will have a localized state. If I perform some rotation, like a passive rotation in my coordinate system, that won't affect the localization of where my system can be found. But if I translate my system from one point where it's localized and I compare that to some other point, I won't have any overlap with that system. That is to say, I can find my system somewhere. And then there's just a small regularity condition to ensure that I can apply Lorentz boost. And what I get from these sets of axioms is just the exact same localization scheme you have from non-relativistic quantum theory. So I have some L2 inner product, which I can interpret in terms of a probabilistic measure. I have a Fourier transform of my wave function as before, and I have a position operator that has the standard form with respect to this inner product. Everything is all well and good. But there are a number of issues then if you try and adopt this localization scheme. First, we only have this localization scheme, this Newton-Wigner description, defined on space-like hyperplanes of simultaneity. It's only defined instantaneously. And this will be a serious issue that we will see going forward. Other issues that have been identified is that our localization is not Lorentz invariant. If I have the system localized and I boost to a different frame, it will no longer be localized in that frame. And if I try and time evolve my system, I'll immediately delocalize that system. So what this is telling us is that there's some incompatibility between our Newton-Wigner localization scheme and microcausality. And this is also articulated in a number of no-go theorems that we'll get to. But before that, I want to turn to this other conception of localization. This conception of localization as it's defined in space-time, not just in space. And here, another of Wigner's students, called Phillips, a bit later than Newton, tried to answer this question. And there, the issue is that orthogonality is incompatible with this notion of a Lorentz invariant description of where things can be found. So what Phillips tried to do is just to replace this orthogonality postulate with Lorentz invariance. And that's all well and good. And what you get from this is a different kind of structure that's naturally associated with everything. You get, if you adopt the Klein-Gordon inner product, you get some Lorentz invariant notion, this Lorentz invariant wave function, where you now have some integration measure appearing. And according to this inner product that we've defined, the position operator will look as before in its standard form. But this localization scheme has a number of serious issues. because we've dropped this orthogonality, we now will always have some non-vanishing overlap of where things can be found. We don't really have a localization scheme anymore, at least nothing so proper, nothing so strict. But even more seriously, the observables that we want to define don't really exist. If we try to define a position operator, then, at least for the spin zero case, it's no longer self-adjoint, it's non-normal. And the inner product that we've defined cannot be given a probabilistic interpretation. We don't have Born's rule. All of these issues were known back in 1964 when Phillips looked at this stuff. And in more recent times, in a more formal mathematical approach from algebraic QFT, they've also come up with an equivalent approach called modular localization, which was reviewed recently by Uenaga. They find the exact same issues that Phillips found here. We have some non-orthogonality, we can no longer define self-adjoint position operators, and we have issues in defining a probabilistic measure. We have to give something up. There's a number of no-go theorems that also try and talk about this seeming conflict between where things are and notions of causality and dynamics. A particular one known in the literature is called Malament's theorem. If we want to talk about measurement, say in the forms of projectors, strictly localized to some volume, and we have some fixed foliation of spacetime, which could be a Minkowski spacetime or some globally hyperbolic spacetime, then we have to give something up again of these four things in this no-go theorem. Either where we have energy being bound from below, we have spacetime translation covariance, we want to have some notion of strictly localized observables or projections, and we have microcausality between different regions in space-time on different hyperplanes. The usual answer is just to stop here and say, okay, well, A, B, and D all make perfect sense, so let's just give up C and move on. But things really aren't that simple. We're actually missing something that's quite profound. And this something is actually captured, I think, a bit more explicitly from another no-go theorem, a bit of a stronger no-go theorem by Hegerfeld. And Hegerfeld's theorem is saying exactly the same thing as Malament's theorem, but it's also saying that we can have a notion of localization, but the localization is only instantaneous. Again, if you want to try and time evolve the system, our system will immediately delocalize. So what's going on here? Well, this is a bit more than just defining a position operator of where things are. It affects all observables. I'm just going to skip on ahead because I'm running a bit out of time. The crux of the matter is an antinomy, a conflict between two central things. We want to have Lorentz covariance. We want to have causal dynamics. But we also want to have a notion of states and observables. We want to be able to have some predictions within the formalism, and ideally, these predictions would happen at some point in time on some space-like hyperplane. But there's this antinomy, this conflict rests on an essential confusion, which is that we're restricted to only talking in one formal description. There's an either-or of this three-dimensional Newton-Wigner description or this four-dimensional space-time description, when in fact, both things are in fact compatible. And this is actually clarified or elucidated very nicely in this review by Alex Bloom, who emphasizes this point on the foundations of relativistic quantum theory, that what all these formulations that we're used to, such as scattering, come back to is this problematized notion of an instantaneous state in the formalism, and how we want to replace it with some notion of an overall process. And so this is the final slide. The basic idea is that we're used to having some space-time description as it occurs in, say, this region M12. What we want to have is a notion of instantaneous surfaces at some moment. We want to add back in something that appears to be missing in our description of quantum field theory. And with that, I'll end my talk.
Any questions? Then maybe the next speaker.
Yep. Evan, but it's a bit more partisan question. Why do we care about having an operator, in a sense, self-conjoined thing, the spectral projection, and not just POVM, which gives you approximate localization? Because even in normal quantum mechanics, if we want localized things in phase space, we need POVMs which are somewhat vague, and we just, not one eye, not another eye, two half-open eyes. So why not here? So what's wrong with the idea?
So the exact same issues that affect projectors also extend to BOVMs. Melon-steric also extend to BOVMs. And there are no issues, again, defining colors and measures for various BOVMs. So the hope is that working within the solidization team, you're still addressing these issues.
We have no time for further questions. Let's thank the speaker here. The next speaker is Shiri Lee. He's going to speak about the quantum armor formula for the quantum radiation of single electron wave.
Okay, thank you. First of all, I would like to thank organizers for this chance of sharing my recent results with RQI people. I have changed my title a little bit. I will explain in my last page if I can reach that. And so, today I'm going to report our results on quantum radiation of a charge at rest and quantum radiation of a uniformly accelerated charge. And before that, I will give you some motivation and some brief review on single electron wave packets in quantum electrodynamics. Okay, so quantum field theory in curved space are mainly applied to cosmology and black hole physics. And unfortunately, we have only one universe and we cannot adjust the parameters very much. And for black hole physics, the situation is even worse because we don't have quantum black hole in laboratories. So this is why we need analog gravity. So the more the more I know, the more detail I know about those physics for quantum field theory in curved space, the less convincing it is to me. So I really need something to anchor to make myself more comfortable. So one of that thing is the Unruh effect, which occurs which is supposed to be occur in flat space-time. So I'm interested in this kind of proposal in which charge or electrons are accelerated by electromagnetic field, and then we can collect the signal, the quantum radiation of the accelerated electron and see the information about the Unruh effect inside. So to describe this kind of system, we introduce quantum electrodynamics. So here, we don't need we don't need to start with Dirac equation or things like that, because here we don't, the most powerful electromagnetic field can only give energy density much below the Schrödinger limit. So the one particle interpretation for electrons is okay in this kind of proposal. So this is our starting point. We have relativistic particle moving in space. We have electromagnetic field, and we have a gauge phasing term, and we have a delta function like interaction, which is similar to the en route DeWitt detector. So, following the standard wisdom in quantum field theory in space, we split the dynamical variables into the classical part and the fluctuations about that classical solutions. And from here you can see this is also a toy model for gravitational decoherence we are considering. And so later we will quantize the fluctuations and deviations from the classical solutions, and then expand. So we insert this expansion into the action and expand it up to the quadratic order and start to calculate. Okay, so here we have a system with quantum mechanics of single electron and quantum electromagnetic field. And so the whole calculation would be proceeding in the context of open quantum system. So by virtue of the linearity, we can do this operator expansion, and then we can calculate these mode functions. And if you solve these equations for mode function consistently and insert them into this formula, then you will get the symmetric two-point correlators in the coincidence limit. Then you can calculate the reduced state of the system, and also the later we are going to calculate the expectation value of stress energy tensor. Okay. So there are two kinds of divergences if you really do the limit. The first one is when you do the mode sum. You really don't want those high energy fluctuations to make your system getting pair production of electrons. So you need to suppress them, and it's reasonable to choose the high frequency compression as the Compton wavelengths or Compton frequency, things like that. The other corresponding to the time resolution or the uncertainty of time pegging at the initial moment and the final measuring moment. And we found that this uncertainty or this time resolution cannot be, it has to be much larger than the fundamental cutoff. Otherwise, you cannot see the Unruh effect. And so, luckily, we find that in electron interference experiments in electron microscopes, we got sufficient information from their technical data. And so there we learned that we got a temporal frequency of electrons out of the field emission electron guns. So we find that it's indeed much greater than the Compton time. And so we put these parameters and as well as other parameters learned from Tonomura's famous paper. Then we find that we can calculate the purity of the electron, flying electron, when it hits the image plane. The transverse degree of freedom has basically about half of the purity, and so it's quite mixed, but not pure, not mixed. It's something in halfway. So we used to think that these field fluctuations may have blurred the interference pattern in these famous pictures. However, recently I realized that the purity and interference visibility is not monotonic. So let me just withdraw this statement until we do the further calculations. Okay, and we also apply this to uniform accelerated charge, and then we can calculate. Also, we can calculate the purity, and we sadly found that if you want to extract to distinguish the unruh effect from the transverse degree of freedom of the electron wave packet, then it's basically hopeless. Okay, so this is the new thing. So quantum radiation. So to calculate quantum radiation, we apply this formula. So we calculate we learned this formula from Roerlich, famous book. So at the classical level, you just insert T mu nu to here, and then you do the calculation. You will see that for a particle at rest, this gives you the Poynting vector. And for uniformly accelerated charge, this gives you the Larmor formula. And you can see that the Larmor formula derived in this way is a constant. It's a stationary, in a stationary state. So at the quantum level, we replace T mu classical stress energy by the renormalized expectation value of T mu nu. And so if you do this, if you derive the quantum version of the stress energy tensor, then you will have some gauge fixing terms included. Fortunately, when you go to now infinity, these terms disappeared. So we only need to calculate this, which is the 2-point correlators of the field. And so let me skip this. Okay, so this is the result. So quantum radiation of the electron at rest is exactly 0. The p part, meaning that in our specific factorized initial state, the p part are those corresponding to the initial state of the particle, and the f part are those is the contribution from those things depending on the initial state of the field. Okay, so P for particle, F for field. Now, the P part contributes no radiation power, and F part contributes 0 too. But we have to check that all the divergences cancel, and other large numbers do not contribute. Okay, so another thing we learned from our result is that bound fields, not going to now infinity, depends on gauge as well as initial conditions. And if we shift the wave packet, the peak of the wave packet off the classical trajectory, then the quantum correction would be a dipole field in the far zone. And this also tells us that the field in the near zone is not reliable because, for example, this one, the singular point will be still around the classical position rather than the peak of the wave packet. Okay, so let me just tell you some results. -1 minute. So regarding to the uniformly accelerated electron, the F part and P part give me a long time behavior in which we have exponential secular growth in proper time. And this tells us that our approximation breaks down. And so let me conclude my talk by some comments on our final result. So first, information about initial states never decays out in this approximation. And second, early time transient radiation like this, like this. It can be very large. It can be almost comparable to classical result. It's typical for this kind of suddenly switch on coupling. And this is really the case. This is physical well, we believe this is physical in Tonomura's electron microscope. Number three, the long-time secular growth is not rare in non-equilibrium quantum field theory. So this is why we cannot write down a stationary quantum Larmor formula. So I have to change my title. And also this tells us that we should not trust our late-time results, since nonlinearity protecting the reparameterization symmetry is not considered here. Finally, do we need to introduce higher order correction or resummation? The main problem is that I don't have PhD students, so I have to do this by myself. So we will do this, but in a very slow speed. Okay, thank you very much.
Thank you, Shirley. Is there any question? Okay, this is complete. If not,
Thank you. Oh, sorry. Oh, okay. Oh, right.
Okay, thanks very much. I'll be talking about a very recent paper with Joey Bojowald. There. Oh, right. Yeah. So the basic idea is that a quantum object is extended because there are fluctuations and all kinds of things. So it should be subject to tidal forces if it's in a gravitational field. And we have methods to evaluate this. For QFT people, this corresponds to a geometric optics approximation. So there's an alternative way to derive results. And the basic implications for now, entropy and purity acquire weight. So we'll see how that happens. And complete description, at least on the semi-classical level, requires non-Riemannian geometry. This is the starting point. So that's been used in other cases with more standard quantum information methods, mainly focusing on time dilation because it's proper time functional. And our new strategy replaces the wave function evaluations with a geometrical formulation of quantum mechanics, which pairs nicely with the geometrical nature of general relativity. So here it is, that's the geometrical formulation. The top line is a standard equation for Hamiltonian evolution of expectation values in quantum mechanics. And now, geometrically, we first introduce a Poisson bracket. That's not classical, it's not on the classical phase space. Instead, we view operators, like O1 and O2, as functions on the state of, space of states. So they're functions of rho, some pure mixed state. And so the function is defined by standard expectation values. And the commutator on the right in an expectation value then implies all the requirements we need mathematically for a Poisson bracket. So there are no coordinates at this point, there are no derivatives by q's and p's, but it's antisymmetry, Jacobi identity, and so on. So it's mathematically it's a Poisson bracket. And for a mathematician, a Poisson bracket defines a geometry. There's no metric, it's not Riemannian, but it's still, you can see surfaces and so on. So that's what's going to be useful in this combination with general relativity. The effective Hamiltonian is one example of these functions. So it's the expectation value functional of the Hamilton operator. And then the bottom line is just a combination of these definitions, and it's completely equivalent to the top line. So the quantum mechanics evolution is reformulated as Hamiltonian dynamics on state space as a phase space with the Poisson bracket. So it's a Hamiltonian vector field on the right. Now, to work with the Poisson bracket, we usually need coordinates. And so that they're not unique, but the useful set is given by basic expectation values. Let's assume we have some basic operators Q and P. And then central moments to arbitrary orders to get all the infinite dimensions in our state space. So these are convenient for physics evaluations. They're not convenient for the Poisson bracket because they're not canonical. We don't just have zeros and ones on the right. But the Casimir-Dabur theorem tells us, at least locally, we can always derive canonical coordinates. So Q's and P's, which have Poisson brackets 0 or 1. And then in general, if it's not symplectic, we also get conserved quantities, Casimir functions in the Poisson terminology, which are conserved for any Hamiltonian. So it's 0 Poisson brackets with any Hamiltonian. Unfortunately, the theorem is not constructive. It's an existence theorem, so it's not always easy to find these variables. Here's one example for these second order moments. So this has been rediscovered independently many times in quantum field theory, quantum chaos, quantum chemistry, and quantum cosmology, and there may be more examples. So for a single pair of degrees of freedom, S and P, so the new configuration and momentum variables are related to the position fluctuations and the covariance. And then the momentum fluctuations introduce this conserved quantity C, which is related to the uncertainty relation. So that's been known. It's more tricky if we go to more degrees of freedom or higher orders. This some time ago with other students. And the main example I'll use here is for 2 classical degrees of freedom. So we have x1, x2, p1, p2. x1 or delta x1, delta x2 still define the first two configuration variables. Beta on the right is another canonical variable which is related to correlations. It has a momentum which will appear later, also appears down here. Momentum fluctuation, so delta P1 looks almost like what we had for a single degree of freedom. But now this U1 is not a conserved quantity anymore, it's dynamical. And it has this complicated relationship with 2 new momenta, P alpha, P beta, and in this case 2 conserved quantities, C1 and C2. Everything that follows will mainly refer to the big square root here, which is the most interesting part. Now, quantum information, so we know that purity is conserved for any Hamiltonian, so it should be a function of C1 and C2, and we'll see how that works explicitly, and then also what the remaining terms are. Now, to get the geodesic, we apply this to the geodesic Hamiltonian from this proper time functional. It's also constrained, but I'll skip those details. And so we get the effective Hamiltonian on state space by evaluating this expectation value of g pi pi. And this brings in all kinds of moments where we insert the previous mapping. So x and p are quantized, g itself is not quantized. Now the mapping then introduces this square root. That has several implications. First of all, it's not quadratic in p alpha or any momentum. So that means the expression, the proper time functional, is not quadratic. There's no metric, it's not Riemannian. So that's where we have to generalize geometry, but it's an example of Finsler geometry. So this is still captured by these expressions. There's some quadratic limiting cases. C1 equal to C2 turns out to be forbidden, or p alpha equal to 0 would be the Gaussian case. Now, more details about the quantities. So this can be compared, everything's related to moments. So if we use the covariance matrix, and then the symplectic eigenvalues are strictly related to C1 and C2, which tells us the first claim on the previous slide, C1 cannot be equal to C2. Purity has this specific relationship with C1 and C2. It appears in this square root, which appears in the geodesic equation, so that's how purity acquires weight. Entropy, it's more complicated. One example, at least for beta equal to pi over 2, is logarithmic negativity. Similar square root appears, but now there's a p beta term as well. And so entropy is described by the Minkowski distance. In this diagram, the central region has 0 entropy, so it's unentangled. And then these red hyperbolae separate entangled from unentangled state. So to conclude, this geometry gives us a more detailed relationship between time dilation and not just momentum fluctuations, but additional separate quantum information parameters. It's also applicable to tidal forces and geodesic deflection because there's the full geodesic equation, so we can use Hamilton's equation to get the geodesics. And we've seen it requires generalization of Riemannian geometry. One open question, so we've been able to identify all but one of these canonical parameters as quantum information variables. And this alpha, we've only seen p alpha so far. Alpha, we don't really know what that is. We have an expression in terms of moments, but we don't have a good interpretation. So if anyone knows anything about what this expression could mean, please let us know. It's distinguished because it's the only parameter left, so we can't apply any canonical transformations anymore. We want to preserve the others. But quantum information is still unknown. So thank you for your attention. I think it just died.
Thank you very much. Other questions?
Okay. The battery died. I think the battery died. I got a warning.
Okay.
There's nothing.
In the meanwhile, the next event will come.
Oh, it should. I got a warning. I don't know what happened.
It's not charging, okay.
All right.
Microphone?
Oh, yeah.
Uenaga, who will speak about quantum equations for finite time interactions. Please, the stage is yours.
Thank you for your introduction. Oh, sorry. Thank you to the organizers. Hello, I'm Uenaga. I'm a master student at Fischer University. So today I'd like to talk about the treatment of quantum random equation for finite time interactions. Okay. Oh, sorry. And the first part is I describe the non-relativistic settings. And so this part is based on our recently preprint or archive, so this paper. Okay. And so the quantum random equation describes time evolution of a system interacting with its environment. So in this study, we consider such a quantum system. The system is a single harmonic oscillator, and the environment is modeled as a collection of n-harmonic oscillators. And the system interacts with the environment through linear coupling. So this setup is known as a Caldera-Leggett model, and which widely used because it allows for analytical treatment. And by throwing the Heisenberg equation for each quadrature of the system and the environment, we obtain the quantum random equation. So this is the system's position operator, and so system's frequency. And so this term is called the memory kernel. Memory kernel means how past interaction influence the present dynamics. And so this term is a noise term induced by the environment. So the reason why we focus on the quantum random equation is that the standard approaches like quantum master equation or perturbation method often rely on the approximation, for example, assuming weak coupling. However, quantum random equation does not need these approximations, and so it is a tool to study strong coupling and non-equilibrium dynamics in a non-perturbative and non-Markovian framework. Okay. And so it is our motivation. So in previous studies, it assumes that the system constantly coupled to the environment for an infinitely long time. So this assumption is crucial for solving the quantum random equation analytically. However, in real physical process, the interactions are often finite duration. So our motivation is to understand the system's dynamics and the finite time interaction in non-Markovian framework. And the solution to quantum random equation in this situation is useful to studying various phenomena like quantum thermodynamics and entanglement harvesting. Okay. Let me introduce our setup. So we consider this open quantum system, and so system is a single harmonic oscillator, and the environment is modeled as a collection of n-harmonic oscillators. And in the end, we take the limit, so this n to infinity, so the environment becomes continuous. And so this is the interaction Hamiltonian. So to model a finite time interaction, we introduce a time-dependent coupling into the interaction Hamiltonian. And so this is a switch function that controls when interaction turns on and off. And by throwing the Heisenberg equation, we obtain the quantum random equation. So the main difference is that the switching function appears here and appears here. And so switching function appears here, so the this term's time translation symmetry is now broken. So to solve the quantum random equation, so we consider in previous study case. So this case is the switching function assumed to be a constant in time. So in this case, so this term's time translation symmetry recover, and we can solve this equation using Laplace transform and inverse Laplace transform. And the general solution written like this form. Okay? And so this G term represents the time evolution of the system, and it is defined as this term's inverse Laplace transform. Okay? And so return to our setup, so we consider the finite time interaction, so the switching function is time dependent. So in this case, we can no longer apply the Laplace transform course, so in the previous study case, so this term's time translation symmetry allows us to apply Laplace transform using a convolution property. However, in our study case, so this term is not time translation symmetry, so we can't apply the convolution property. So the problem is that so we don't know how to compute this Laplace transform in general time dependent coupling. So to deal with this process problem, so we adapt the switching function represented as a train of N-Dirac delta switches. So this method is inspired by these previous works, and so now T is a total interaction duration and N is a number of delta switches. And so this KTK represents interaction strength at each interaction time. And thanks to this delta switching approximation, we can compute this Laplace transform exactly. Okay. And so to apply the Laplace transform and the impulse Laplace form to the equation, and we obtain the solution in finite time interaction. So this G term represents the time evolution of the system, and it can be expressed like this form. And the first term represents the free evolution of the system, and it propagates from the initial time to now time t following sine or cosine-like function. And this second term is more important as physical read. So this component of this term has a physical meaning, and so this term represents the propagation from initial time to some interaction time ti. And so these two terms reflect the memory effect. It describes the time evolution of Ti to Tk under the influence of environment. Okay. And so the next slide I will explain the more specific dynamics about the function of z. So this diagram shows the full dynamics of the time evolution function z. So here we take the n equal 4 delta switching case, and the full dynamics reflects the combination of these effects, like so free evolution and memory feedback from the environment. And one of the interesting point is here that the full dynamics can be visualized like this. And so to conclude part 1, we now demonstrated whether our solution can agree with the continuous switching case. So we take the G, we compare the G terms 1 second after interaction begins. On the left hand side figure shows the value of the G and GFP term in front of P0. And the blue line shows the quantum switching case, and the orange line shows the delta switching case. As you can see that, so the delta switching method can closely approximate the solution described with the continuous switching case. So, and the next part we consider the relativistic setting. And so this is the ongoing project. And so first let me introduce the setup. So we consider the system as a harmonic oscillator type Unruh-David detector, and the environment is a quantum scalar field. And so this is the interaction Hamiltonian. And so throwing the Heisenberg equation, so it leads to the quantum Langevin equation. So in this case, so the memory kernel is described as a retarded Green function, and so we consider the environment as a quantum scalar field, so the field operator is smeared by the switching function. And finally, we demonstrated that the same case, so so we consider the setting the Minkowski vacuum, and we compare the value of z 1 second after interaction beginning. So the figure on the left shows the result of the constant switching case and delta switching case. And as you can see, we found that the delta switching method is effective even relativistic settings. And so this is the conclusion. We have derived the solution to quantum Langevin equation for finite time interactions using a train of Dirac delta switches, and we found that this method is valid for non-relativistic and relativistic settings. As a future work, we want to apply this method to relativistic auto engine to explore how causal propagation affects the cycle completion and positive work extraction. And another direction, we want to apply this method to the entanglement harvesting, or we want to analyze the stability condition. That's all. Thank you for listening.
There is time for some questions.
Thank you for the talk. So since you're using a harmonic oscillator as your system, that can be solved non-perturbatively, have you considered replacing your system with a qubit and then doing the Dirac delta pulses and getting some sort of evolution equation for that instead?
Sorry, one more.
Have you considered using your Dirac delta train method to get to use it on a qubit instead of a harmonic oscillator, coupled to a bath of harmonic oscillators or fields?
Sorry, so let's discuss it later. Okay. So let's discuss it later. Okay. So I could. Sorry, I couldn't catch your question. So.
Can you repeat? Okay. So your model, you have a harmonic oscillator as a system, and then a bath of harmonic oscillators.
Yeah.
With your method, could you use instead a qubit as your system and couple that to a bath of harmonic oscillators and get a similar equation?
Okay, thank you. I see your question. So maybe it could system system considers qubit.
Thanks.
Any further questions? Okay, if not, let's thank the speaker again. So the next talk is a remote talk by Grothus. Yes. Do you hear us? Martin? Martin? Do you hear us? Can you speak? So, try to understand the talk as well.
That's not good.
Can't hear you. Yeah. Okay, go on saying something.
Yeah, Martin is frozen. Okay, so maybe you can just try to switch the order of the speakers, given that both of them are online. Anjana, could you try screen sharing, please?
Yeah, just a second.
We also, can you try speaking before that so that we test your audio?
Am I audible now?
Yeah, we can't hear you on the room, but your audio is working. Now the issue is on the room. I can hear it here. So now we need to get IT. Sorry, 1 second.
Can you hear me now?
Hello, Martin, you've reconnected. I'm assuming that your audio is working now. Can you try speaking?
Yes, can you hear me?
Yeah, we are having some technical difficulties in the room. So we're gonna have to get IT here. So please give us a couple minutes.
Okay.
Hello, can you please try speaking, Martin?
Yes. Can you hear me well? Or are there still issues with the technical difficulties? Because I see that Zoom seems to be registering when I'm speaking to you.
Sorry, Martin. Okay, now it's working. Everything is working, so I'm gonna give it back to Gaetano, and we can proceed normally.
Thank you. So go on, Martin, start.
All right. Even though it's a little bit unusual to not see anyone and give a talk, thanks for joining. I give a talk about my project in routing quantum control of causal order with Lister Abbott and Cyril Monsier. And in this project, I'm looking into the overarching framework of process matrices and higher order transformations, which you might have heard on in the context of indefinite causal order. And I'm connecting two, could say, related frameworks or sub-frameworks of this to one another. And these are the quantum circuits with quantum control and the rooted quantum circuits. So in this talk, I give you a very brief introduction, and then I'll briefly present my results. So as you are probably familiar, in quantum mechanics, there are channels as first-order transformations, phi transforming states into states. Rho becomes rho prime, and they have certain properties. So in quantum mechanics, these are completely positive and trace-preserving maps. In classical mechanics, it would be linear stochastic maps, and we will talk about probability distributions rather than quantum states. However, we can bring this one step further. So we can conceive a super channel which transfers a set of valid channels to another valid channel. These will then be linear in the channels and therefore have some additional properties which ensure that indeed the resulting object will always be a channel no matter what you specify. And the Choi representation of these superchannels are known as process matrices, which you might have heard of in the context of quantum gravity, maybe. However, I would like to take a more computer scientific approach a bit and see this really as a method of computations or of mathematics at first. So a simple example of a superchannel is a so-called quantum comb, which is basically just a standard quantum circuits with slots. We have local operations, A1, A2, and so on to AN. And there's a comb, which you see like from the form, which does some transformations in between. And we can plug arbitrary operations in these slots and receive a valid total channel. However, in this case, we have a fixed order between A1, 2, and so on. And while this is a very natural and simple way to form a channel, it's an interesting question. What's actually the most general form such a superchannel can have? And this brings us into the study of the field of indefinite causal order, where these operations orders is not necessarily predetermined, but something more complicated is going on, even though still each of these operations is used once and only once. I won't go into the phenomena of indefinite causal order much in this talk. You might have heard about the quantum switch, and we've seen this a little bit later. But there have been a few examples been studied, but also some frameworks have been proposed. So there are quantum circuits with quantum control, which allow for coherent control of multiple temporal orders of operations in superposition. And there's also a framework of rooted quantum circuits, which is a more compositional and diagrammatic representation of alternatives. And there are many more frameworks, but in the last few years, a lot of these frameworks have been proposed to understand this phenomena, but they haven't been connected, so we can't really transform things from one framework to one another. And this complicates the study of phenomena, which are particularly interesting in the context of indefinite causal order, like dynamical order, where the operational order of two agents, Bob and Charlie, depends on the choice of another agent, Alice, or of consistent intrinsic and causal time loops, which are possible in generic processes or supermaps with 3 agents or more. And so to give a very brief overview, the QCQCs, the quantum circuits for quantum control, are a generalization of this quantum comb idea, where in each slot there's a superposition of agents acting, such that in total each agent is acting precisely once. So we have a bottom-up framework to construct some supermaps with acyclic information flow, where operations AK alternate with internal isometries again. We still have an ancillary system, and we now have a novel register which keeps track of which agents have already acted, so we know which may still act and which already have basically lost their chance for each branch of the superposition. And these isometries also take care of the routing to choose which agent will act next. And this class is particularly interesting because there are various results recently which indicate that this set of quantum circuits with quantum control corresponds precisely to the set of supermaps realizable within a fixed spacetime. And there's been some work to generalize this as well to some more dynamic spacetimes, but I don't know about the results of these studies. And another framework, which is a little bit different and a lot more diagrammatic, is the framework of rooted quantum circuits. This is a compositional framework which allows to construct unitary process matrices. But in general, these may violate so-called causal inequalities and also represent time loops, for example, which is not possible with the QCQC framework. The framework makes heavily use of the direct sum structure, which is possible to exhibit between quantum states. So if we consider a composite state, it must not necessarily be in a tensor product form like this, have 2 Hilbert spaces, but we can also have some non-trivial direct sum of states. For example, if we have a state either going to the left wire and to the right wire, a photon, and on the other wire we have the vacuum, then this is a direct sum state. Either the photon is left or it's right, but it's not in both of the wires or none of them. And this structure is usually not that apparent in standard quantum circuits. This rooted graph in this rooted graph, then each combination of indices showcases a possible alternative, and there are some consistency conditions ensuring which are sufficient to tell us that each process represented by this graph is actually valid. And this is in particular that each node is visited exactly once, and that there are no paradoxical time loops induced by this index structure. And these are nice because, in contrast to like standard circuits, these are agnostic of the dimensions. So this represents a full class of processes and also has some more freedom in the agents, which I don't have time to go into. So now seeing two simple examples for two agents, it's a natural question: how can I transform between these two? And this is the contribution of my work. And to representing QCQCs using rooted quantum circuits, which is basically to incorporate the internal isometries themselves also as nodes in these graphs, such that internal operations alternate with agent operations. Then the control register is reflected in these indices, which record the set of agents already visited, replacing effectively the control register from the QCQC picture. And at each Vn+1, the index is modified to take more additional values, to take the agent next to be visited into its value. And with this, we have now, which might be surprising at first, a canonical representation of all n-party QCQCs from a single rooted graph. Now we can, by associating Hilbert spaces with the arrows and factoring out the target spaces, we can effectively reproduce the QCQC and provably from this picture. This, of course, is only for n equals 2, for two agents A and B, but we can also do similar things for three agents. This might be a little bit unwieldy at first, so I've took the liberty to color it a little bit. So you can see the non-trivial path to this through this diagram, and if the agents are acting in order A, B, C, would be following from V1, specifying A as next agent to V2, going to B as next agent to V3, to C, and then to V4. And there are, which I would like to point out briefly, these representations are not unique. For example, there are this is also a representation with some more arrows, which has some upsides and some downsides by making the ancillary systems explicit. And in my paper, I have some more examples of this and show some upsides and downsides it brings to look into this. So finally, I'll give a very brief summary. This research will appear as a preprint on the archive within the next few weeks. The main result is that we have a representation of all n-party QCQCs using a single rooted graph, which also by composition gives that all processes in a fixed spacetime have a representation as a rooted circuit, which hasn't been known before. We also figured out that the internal nodes can sometimes be omitted in the rooted graph representations, but generally are indeed necessary, and that there's some trade-off between the complexity of the rooted graphs and the maps we need to plug in ultimately, which I haven't, sadly, due to time constraints, have time to go into more. In the future, we'd like to stress to go further in this directions by characterize and represent subclasses of QCQCs using rooted circuits, furthering the intuitive understanding of these processes, and generalize some lessons for dynamicality of causal orders to more general processes which may have time loops, which in the presence of time loops, what even an order is becomes an intriguing question. And finally, a more far-fetched question is to figure out a broader class of rooted circuits, which would correspond to QCQC than the few examples of generic graphs which we provide in this work. And with this, I conclude. Thank you for your attention and going along the ride, and I'd be happy to answer one or two questions if I have time.
Thank you, Martin, for being so much on time. Are there any questions? We have time for a couple, if any. Okay, apparently there are none, so let's thank the speaker again. Now,
have a nice weekend.
Now it's time for Ananya Krishnan.
Yeah. Hello, am I audible?
Yes, very
Hello. Yeah. Okay. So let me just share my screen and I hope it is visible. Let me just start presenting.
Yes, yes.
Okay.
So,
Okay. So I hope the slides are also moving.
so yes. So the title is Derivative Coupling in Horizon Brightened Acceleration Radiation, a Quantum Optics Approach. Please, the stage is yours, Aniana.
Okay, thank you. And hello, everybody. Good evening from India. I am Anjana, and this work I have done with my supervisor, Ashmita Das, and also Shunandan sir and Soham. This work is submitted to the PRD, and its preprint is available on arXiv. So with that, let me begin with my talk with the concept which we are all familiar with, and that is the concept of vacuum, which is not absolute, but rather an observer-dependent state. So this in turn led to the phenomenon of particle production in vacuum, uh, which we have a lot of examples of, like the Unruh effect in the flat spacetime or the Hawking effect in the curved spacetimes. These were proposed in 1970s, and a few decades later, in 2003, Scully et al. Tried to perceive this particle production phenomena using a quantum optics approach. And then in 2018, they extended this, perception to a near black hole region. So the thought experiment, the setup of this thought experiment was as such. We have the Schwarzschild black hole, which is non-rotating and chargeless, and its event horizon. And there is a mixture of fields all around it. Now, a cavity is prepared such that inside this cavity, there is only real scalar fields. Here we can see there is a shield in here. The shield will restrict any Hawking radiation, possible Hawking radiation, to enter our system. Also, we can see there is a mode selector in here. This mode selector will allow only certain frequencies, field modes inside this cavity. So let's just say we are choosing only one single frequency inside this cavity, which is nu. Now, suppose a line of atom is falling freely, passing through this cavity. And these atoms / detectors are two level, having a ground state and an excited state. And let's just suppose that its frequency is omega. Now, when it is interacting with the field, due to the relative acceleration, what will happen is it will jump to an excited state while simultaneously emitting a radiation. This radiation in flat spacetime is virtual because it is quickly reabsorbed by the atom. But here we have to understand that we are in a non-inertial frame. So there is a probability of this photon not getting reabsorbed again, but rather manifested into a real one. So this is what they tried to find out, whether the probability of getting such transition is 0 or not. So the mathematical formulation of such a setup is they started with a Hamiltonian, which included the coupling constant G and the detector monopole moment of the detector and the field in here. And what they started with is a 1 + 1 dimension. They proceeded further with the transition amplitude and the transition probability, which is non-zero as we can see, and it showed a Planckian distribution. So this was the standard literature. But we all know that in lower dimension, when the detector is minimally coupled or linearly coupled with the field, there is an amplification in the infrared divergence. So one of the methods with which we can reduce this is derivative coupling. Derivative coupling basically means that we are coupling the detector with the time derivative of the field. So now the modified Hamiltonian will look as such, where pi is the conjugate momenta. The conjugate momenta, as we can see, it includes the time derivative of the field. Also, it includes the curvature of the space-time. This curvature can be, this metric can be easily obtained by solving for the Schwarzschild line element as I have shown in here. So with this Hamiltonian, the transition probability will look as such, and the plot will be as shown in this. Now it will be much more clearer if I give a side-by-side comparison of both the standard literature and the derivative coupling. The first thing that we notice in both of this is there is an enhancement in the transition probability for the derivative coupling. And number two, in the expression, we don't see any omega dependence. So I will come back to this point in the remarks slide at the end, but I just want you to keep this in mind. So we did not just stop here. We proceeded further by now considering the aspects of the detector. So we initially considered the atom to be point-like. And if it is point-like, we can understand that now it is highly localized. That means it will lead to ultraviolet ambiguities. And also it is idealistic. So it cannot be modeled in real life. So what we tried to do is we gave the detector a smear. This will not only regularize the detector field coupling, but also will help minimizing the ultraviolet divergence. So the smearing function looked like this. It has a Gaussian profile. And what we consider is the atom is falling horizontally towards the black hole event horizon, just to minimize any tidal effect that will be caused if it has been falling vertically. So the modified Hamiltonian is now as shown in here. So with this Hamiltonian, if I try to find out the transition probability, we have such an expression. And here we come across 1F1, which is the confluent hypergeometric function. This means now the transition probability, it indeed depends upon the aspects of the detector. Either the product of L omega, L is the characteristic wavelength or the smear of the detector. So L omega is either less than √2 or greater than √2 according to this expression. And under these two conditions, I get the probabilities for both of these cases as such. And with this, we get the transition probability of this sort. So what we can see in here is there is the enhancement of transition probability for the case where L omega is lesser than √2, the smaller case. So we have found out the transition probability. It is by nature that we move further by calculating the density matrix, the steady state, and also the entropy. So now in total, we have 3 cases, 1 for point-like and 2 for the finite size. So the steady state solution of the density matrix for these cases are as such. What we can see in here is for the point-like and the larger case, we get the same solution. But the different thing which we encounter is for the smaller case, we get it as 0. That means what we propose is now in this regime, the system is not in equilibrium, but rather in a non-equilibrium thermodynamic state. So if we want to calculate the entropy, we get as such. We get the same for the point-like and the larger case, but here we cannot compute it further. So now I would like to summarize and also give certain remarks regarding the work. So we started with saying that in lower dimension, there is an amplification in infrared divergence, which is caused due to a minimal coupling between the detector and field. So this is tackled by using the derivative coupling. So derivative coupling, it showed us an enhancement in the transition probability as compared to the standard literature by Scully. And the other thing which we encountered is there is an independence of omega, the detector frequency. So what we propose is now in this limit, the detector is not coupled to the field, but rather it is coupled with the curvature of the spacetime. So that means the detector is now free to jump to any state. The detector frequency can have a range of frequencies. And that is possibly the reason why we get an enhancement in the transition probability. Now coming to the finite size case, we encountered 2 cases. So let me begin with the larger case. For the larger case, we can see that the product of the characteristic length and omega, it is greater than √2. That means the characteristic length, it is spanning multiple modes of the field, multiple phases of the field. So overall, effectively, it is leading to a destructive interference. And that might be the reason why we are getting a suppression in the transition probability. However, for the other case where L omega is lesser than √2, it will now span only a single phase at the max of the field. And that is the reason why we saw an enhancement in the transition probability for L omega lesser than √2. And the final thing which we noted down was for the smaller case, for this case, we don't get any steady state solution of the density matrix. That might possibly mean that we encounter a non-equilibrium thermodynamic state in this region. So with that, I would like to conclude my talk. And here is the archive link. And also, before I forget, I would like to thank the organizers for allowing me to present online. And I hope to meet everyone physically, considering there are a lot of proposals being made for the upcoming year. So with that, I'm open to any questions that you might have. Thank you.
Sure. There is one here.
Yeah. Hello.
Hi, thank you for the talk. My question was just technical. So how many space-time dimensions were you working in? So you had which?
Okay, so we are working in 1+1 dimensions.
Okay, and if you do it in higher dimensions, do you see similar behavior for the derivative versus ordinary coupling?
Actually, we have not yet tried with the higher dimensions. We specifically did it for lower dimensions because due to the correlation function, the Weightman function in the theory, in 1+5 dimension, we get a divergence, an IR divergence. So we try to tackle that problem for now.
Thank you.
Yeah.
Are there other questions? Maybe I ask one. Is it easy to physically realize this derivative coupling or no?
I don't think so. I haven't checked whether it is physically realized or not, but when we do mathematical calculations, we see that we do get an infrared divergence. So, yeah.
Okay.
Yeah.
So thank you very much. Let's thank the
Thank you.
speaker again.
Yeah.
Okay. The next speaker is Stanislav Kurdzialek. Oh, sorry. Kurdzialek. So the next speaker is Stanislav Kurdzialek.
Some pointer.
Or you going to speak about using adaptiveness and causal superposition is noise in quantum mechanics. This is
Okay. Okay, so hello everyone, and thanks for coming to my talk on Friday evening. Yes, so in fact this is I'm working on quantum metrology, and it's my first conference which has relativistic in its name, so it's a pleasure to be here. I really learned a lot from you. And now I would like to tell you something about my work, and I will tell you about the work which I did in collaboration with Francesca Albarelli, Rafał Dębkowicz-Dobrzański and Wojciech Górecki. It is not the most recent one, but it has something to do with this causal superposition thing, which was also mentioned like 2 talks ago, and that's why I think that you might find it interesting. But first I want to focus on introduction to my field, which is theoretical quantum metrology.
So for some people, the phrase theoretical quantum metrology sounds pretty weird because this is the science about measurement, and now I'm telling you that I'm doing theory. So basically, what we are interested in is that there are these amazing devices like LIGO wave detector, which has also amazing precision, and now what we are looking for is what are the fundamental limitations for the precision of these devices. So obviously, as theorists, we might simplify a lot. So for example, if we think about LIGO detector, we say, okay, this is like Michelson interferometer, and the goal is to estimate the phase theta between two arms. Or if we think about atomic clock, then we say, okay, this is again some phase which is imprinted in a qubit, and we want to estimate it. But in fact, we are not as naive as you might think, because we also consider noise. For example, in LIGO detector, it's very important that there are some photon losses. And that's why we don't assume that the parameter that we want to estimate is imprinted on our quantum state in a unitary way. We in fact make much more general assumption that we have some general quantum channel, lambda theta, which is a completely positive map, and it may include noise of any type. And we want to estimate the parameter of this channel as precisely as possible. So the general scheme is the following, that we start from some probe state ρ0, which is described by a density matrix, and it doesn't contain the information about the parameters. So we can, in principle, choose this state as we wish to estimate as precisely as possible. This might be, for example, some state of a photon, which inputs the interferometer, or some spin, which probes the magnetic field. Then we have a quantum channel, which is parameter dependent, so for example, this quantum channel can be an interferometer, right? It acts on a state of our photon or photons, and then what we do, we have the output state. So for example, output state of the photon, or output state of a spin which interacted with magnetic field we want to sense, and it contains some information about our parameter theta. And at the end, we need to perform a measurement to extract this information. So now, since our goal is to know theta as accurately as possible, we can formulate the problem mathematically in this way, that we want to minimize the error of estimation theta over all possible input states, over all possible measurements, and over all possible classical estimators, because we can also analyze the data in numerous different ways. So this problem is quite challenging because you have a lot of degrees of optimization here, and in fact it's very hard to do it with brute force methods, even for small systems, not talking about large systems when you have, for example, multiple photons. So to solve the problem, we need to use some more clever trick. So once again, this is the basic metrological scheme in which we have one quantum channel, and we can input any state to this channel, and this state can be also entangled with some ancillary system, which we can measure at the end of the day, and it can help us in the estimation. And now, if we bound the error of any estimator of theta, it turns out that this minimization can be written as inverse of a so-called channel quantum Fischer information, which is like the central quantity in quantum metrology. And now, actually, there is a way to calculate this channel quantum Fischer information, and it can be done in the following way. So we take our channel lambda theta, and this channel has some Krauss representation. But in fact, it has multiple Krauss representation. Like the Krauss representation is not unique. And now what we need to do is we have to construct such operator where dot denotes the derivative of Krauss operator over the parameter. So it tells us how sensitive is the channel to the parameter. And now if we calculate the operator norm of this sum, then it gives us some upper band for channel quantum Fischer information. But to get the exact result, we need to minimize over all possible Krauss representations. And then we get the exact value of channel quantum Fischer information. This minimization over all equivalent Krauss representations seem hard, but in fact it can be done quite efficiently, at least for small channels, using semi-definite programming. Okay, but this is like the simplest problem you can solve in quantum metrology, because maybe before going to multiple channels, I will also show you some examples. So first, let's assume that we have a channel which is just unitary channel. So we have a rotation of a Bloch sphere with angle phi. Then the Fischer information is just 1 for this channel. But now if we add some noise, for example dephasing noise, which shrinks our Bloch sphere towards its z-axis, then we see that it decreases our Fischer information. And it decreases by a factor eta squared, where eta is the length of the Bloch vector after shrinking. But you can also imagine another type of noise, which is not that dangerous for us. So the noise which shrinks the Bloch sphere in another direction, towards x-axis. And then it turns out that if we cleverly design the input state for this protocol, we can get the same Fischer information as for noiseless case. Okay, but now, in fact, the much more interesting things happen when we consider multiple channels. And then the easiest thing you can do with multiple channels is to just measure them independently. But it's not very exciting, because then you just need to multiply your Fischer information by n. But much more interesting thing is when you consider n channels probed coherently with some input state that can be entangled and that probes all the channels, and then you can also perform some collective measurement at the end. And then if you calculate the quantum Fischer information of these n channels, then it's usually larger than n times Fischer information of a single channel. So this is the reason why it's beneficial to probe channels coherently in many cases. And now in quantum metrology, there are two different types of scalings. One is Heisenberg scaling, where Fischer information scales Sn squared, and it happens when there is no noise, or if there is noise which we can fully correct. The more common type of scaling is a standard scaling, in which Fischer scales linearly with n, but still you might get better constant of this scaling than if you don't use entanglement at all. So for example, if you use squeezed state to estimate rotation phi in the presence of dephasing, you get the improvement by this factor 1 over 1 minus eta squared. If you use entanglement if you use squeezed state instead of probing channels independently. Okay, so this was all established some time ago, but now what was the goal of our work was to check what happens if we consider more general schemes of probing multiple channels. So what we can do with many channels. Apart from probing them parallelly, we can, for example, probe them sequentially, one by one. We can also put some control between channels. We can put some measurement in between which affect the next control. Or we can unitarily control the channel using some ancillary system and then perform some error correction codes. So this is the most general control that is for which the causal order is well defined, and it can be defined by a quantum comp. And this is more general than parallel scheme, because you can always perform swap operation here to simulate any parallel scheme in which entangled state probes many channels independently. And apart from that, we can also add this quantum switch thing, in which we you coherently use different orders of channels probing with some controls in between. I'm not considering the most general process matrix, but those in which I just have some causal superpositions of different orders. So this sets some hierarchy of different metrological strategies, and it was shown in this work that it's like strict hierarchy, which means that you can always have some improvement by going from E to AB and from AB to CS. But now basically our result in this work is that we show that this advantage will never happen asymptotically. So these three schemes are asymptotically equally well, which somehow means that this entanglement is really the most important resource for your quantum metrology, that you don't really need this adaptiveness and causal superposition in the asymptotic limit. And now, just to finish, I will show you some examples. So, for example, for dephasing, these are the bands for this parallel adaptive and causal superposition, and you see that they all converge in asymptotic limit. And here they are not saturated, at least for small n, because for small n we can get exact results, but just for n up to, let's say, 4, because then the problem of optimization becomes exponentially hard. But what is maybe more interesting is the phase estimation in the presence of a damping noise, in which the Bloch sphere is rotated and the noise shrinks the Bloch sphere towards some point, either to the ground state or to some state on the equator of a Bloch sphere, because then you can see that for finite n, you may actually get some advantage from using this adaptiveness and causal superposition. In particular, if you have this shrinking of Bloch sphere towards equator, you can, using these causal superpositions, we already with 2 uses, you can go to the point to which you can only go with adaptive schemes if you use infinite number of channels coherently. So, okay, so even though asymptotically there is no advantage, this is very nice result that if you can only coherently use 2 channels at the time, then this causal superposition schemes allow you to get to the optimal precision. Okay, and so with this, I would like to finish, and like the take-home message is that even entanglement is the crucial resource in quantum metrology, but other resources like using causal superposition-based schemes or adaptive control may also be very useful for finite number of channels regime. Thank you.
Who is going to talk about quantum mechanical analog black holes and analog cosmology.
How short? Okay. The only one. So let's see if it connects. This one is too short, the cable. Okay. No, it's enough. You can hear me, right? You would be, I don't need a microphone. So full screen doesn't work or what? Okay, that's the Acrobat reader. Okay. Does it do something or not? So, does it go to full screen or not? Okay. So, full screen. Maybe this is the wrong window. Takes forever. Okay. Now maybe. It should appear now, but it doesn't go to full screen for some reason. Yeah, of course, usually it works. With most HDMI connectors in this world, it works, but not with this one. Yeah, but I would like to have at least full screen. I mean, like, Okay, I think we have to do without full screen, huh? Now it's doing something.
Okay, so again, the title is one really important analog black holes in analog cosmology.
But now it cuts off something. Okay, let me try first to disconnect this and then, because I mean here it works on my screen, but somehow this projector is maybe from the last millennium. I don't know. Now it goes back to not full screen. That's okay. Okay. Yeah, okay. So thank you very much for coming to my talk. It's still a 2-digit number of people, which is great. So let me begin. It's a bit too much zoomed out. Let me begin just with, so why do we actually caring for quantum simulations of fundamental quantum field theory effects in many-body systems? I mean, the first striking number is, of course, this one here. For an astrophysical black hole, you have 60 nanokelvin. I mean, solar mass black hole. 60 nanokelvin is the temperature, which on top of the cosmic microwave background is not too much. Try to distinguish a thermal signal of 60 nanokelvin from 3 Kelvin, or 2.7, whatever you like. No, I don't need that. So it's of course unobservable. But in a cold quantum gas, 60 nanokelvin is a sizable number. And the Hawking temperatures you can get actually are on the order of nanokelvin in a cold quantum gas. So this is observable in these systems. So this is a string of paper by a Steinhauer group in Israel, which constituted first undebated observations of the fundamental quantum field theoretical effect of Hawking radiation. Other effects were observed, for example, I mean, it's just a selection of groups in cosmology. I will come back to cosmology later. So first of all, what are quantum many-body black holes in our sense here? The Steinhauer BEC experiments are creating, that's why it's blue here, the sonic horizon from which the Hawking radiation emanates in a highly non-equilibrium configuration, at least initially. They sweep a blue detuned laser through the BEC, pushing atoms out of the way, which creates the horizon, from which, with rather high precision, they get indeed the thermality of Hawking radiation into the density-density correlations. What we addressed in our study, the first study I referred to here, is whether finite size in one-dimensional, this is effectively one-dimensional system to avoid turbulence, which Steinhauer studies, whether finite size stationary black holes, actually stationary black holes exist in 1D. Well, first of all, there's a condensed matter fact here. Phase fluctuations in 1D will destroy in the thermodynamic limit. any long-range order. That's a very known thing, known under the name Hawking, or Holmberg theorem. Sorry, Holmberg theorem. Okay, so our setup is the following. As I said, we want to have a finite size BC, but because we want to have just a black hole and not a black hole white hole configuration, which would be unavoidable if you go on a ring, a one-dimensional steady state flow on a ring. What comes up must come down, right? By continuity, you will always get black hole white hole pair. So you need a finite size system, also here with a source and a drain, feeding here and removing here. Else it will never ever be stationary in one dimension. So here's the upstream flow. We keep the velocity constant, and we change, in fact, the speed of sound by changing the coupling. We keep the flow velocity constant, and we change the speed of sound. So what we change here is the Mach number to create the horizon here at xh equals 0. Okay, so that's our setup. What we then use is the usual tool which also Hawking used, namely Bojowald theory, which every reasonable physicist in the world has to use, in my opinion. It's the most powerful theory of any many-body system, in effect. So we decompose the field operator into some background, which here I separate off the constant flow velocity and some chemical potential. I assume a stationary state, so the density here, and here's some fluctuation. That's our field. And the depletion, so the number of particles, the density of particles, which is not the condensate, which is on top of the condensate, which is removed by interactions and other effects, like Hawking radiation, from the condensate is this number here, the expectation value of the excitation density, obviously. So Bogolubov requires that this quantity here is much less than this quantity. That's a very basic self-consistency condition, which Bogolubov requires. I think everyone in this room should know this. So what we keep is depletion less than 10%. Typically, actually, it's only 3% in our study. Okay, so first of all, we studied, as usual, the excitation spectrum of such system. We wanted to know whether the system is actually stable, has finite or infinite lifetime. So we studied this quantity here. We took the imaginary part, the excitation frequency, and defined some lifetime. What you see here is a really messy behavior. There is some stability windows. Note here, this is the inverse thing here. So when it drops down to 0 here, there is some stability windows, some stability points where the thing lives forever. But you see it's highly irregular. Depending on the Mach number, we get, as a function here of downstream Mach number and total size L, we get some relatively irregular pattern. So it's not guaranteed that this thing lives forever, this black hole, this single black hole, in this many-body system. Okay. So what we do now is we do a quench preparation of the black hole. We start actually from interaction 0 to have a well-defined vacuum. Because it's a highly I don't have the time to explain this, but it's a highly non-trivial question how to actually get to a quasi-particle vacuum when particles are interacting. It's a highly non-trivial thing. So to have a well-defined initial vacuum, it's a non-interacting vacuum. We quench from that vacuum. We start from horizon configuration and quench to our desired final black hole configuration with a finite coupling. And we computed the depletion as a function of time after that quench. Okay, so what we get is the following. What you see is here as a function of time until the thing becomes unstable. Stability time is tau, I remind you. What you see is here, there's some front building up with time. This thing here. Well, that's the Hawking radiation, in fact. That's the dynamical build-up of Hawking radiation in this kind of, well, not quite collapse thing, but in this suddenly turning on the sonic horizon thing. That's the build-up of the Hawking radiation front, what you see here, with time. We'll come back to that, how to analyze this more deeply, this Hawking radiation thing. It's a kind of shock front, as you see, which is building up. And we have some oscillations here, downstream. So inside the black hole. You will say, we cannot look inside a black hole. What is that? No, we can look. We are in a condensed matter system. We now have complete control of every point in our system, also inside the black hole, obviously. That's condensed matter, that's physics. Okay, so this is one quench, which is really deep, so a large variation in the Mach number from which to which we quench. We can also do a less deep quench, so the difference here between initial and final, or the difference between this guy here and this guy here is rather small, so less deep quench. And what you see is here, you still get this build-up, which is somewhat diminished, but in fact you get more strongly with the less deep quench, with the less variation of the Mach number, you get more oscillations inside the black hole. The oscillation amplitude becomes bigger inside the black hole. So downstream, that's downstream, this is upstream, this is downstream. Right side is downstream, to remind you, left side is upstream. Inside, outside, black hole. So now, what do we do with this signal which we obtain? We can look at the power spectrum of the quantum depletion. You have seen there's these oscillations, right? Suggests you the power spectrum of the quantum depletion density. This was actually done experimentally already quite some years ago in the Hadzi-Babbage group, Cambridge, for 3D case. And here you can see, this is the left side is an unstable black hole case, and the right side is a stable black hole case. So tau goes to infinity is the right side, the left side is a finite tau. You can see there's a very distinct feature here emerging. This depletion is actually first order correlations. It's a G1 function in effect. It's not the usual signature density-density correlation. It's a first order correlation function, not a second order correlation function. So we see here the depletion spectrum is related to this, as I said, to first order correlations. And actually it's more strong signal. Obviously, to measure first order correlations is easier than to measure the very tiny second order correlations, which are the usual, according to Balbino et al. From 2008, the usual signature of the Hawking radiation. The weak density-density correlations. Yeah, okay. So this was published already 3 years ago. What I actually wanted to talk about in this presentation is a very much newer study, but to which I devote 4 more slides. I was not allowed to change my topic because it was a scientific committee decision that I have to give a talk about this older stuff. Okay, so what I want to do now is some new stuff, which is on the archive since exactly 37 today, 17 days. And this is the following, our analog quantum cosmology. As you know, the hallmark signature of inflation is the power spectrum, 1/k^3 for exact inflation. There is, however, a duality, maybe not completely well known, but some people know it. The so-called Bond's duality, that between bounce scenario, so non-singular evolution of the cosmos, that the thing bounces back and never reaches the singularity, and the singular paradigm, the usual paradigm of cosmology, inflation, there's this duality. You get the same scale invariant power spectrum, so 1/k^3, as long as you are completely remain Lorentz invariant for both the bounce and inflation. That's the Bond's duality. Well, that's the year of my PhD, no relation, but anyway, that's like it is. This is just some animation here. I don't want to explain this now in detail of what is inflation and what is bounce. Okay, the thing is now the following. We go a little bit beyond our previous paradigm with contact interaction gas, and you use a dipolar, so dipole-dipole interactions between the gas particles. They have a sizable dipole moment and contact interaction. The usual localized paradigm of quantum field theory. So we use both dipole and contact interactions. On the left side, you see the Lorentz invariant standard dispersion. You see the Unruh dispersion, which I like to call flat band dispersion, because it's flat over large value of k. That's what Bill Unruh used in 1995 in his famous paper on the Trans-Planckian impact on Hawking radiation. And there's the Corley-Jacobson case, also very popular in cosmology. On the right-hand side, you see a dipolar BC, where this A here is basically the chemical potential. This R here is the ratio between the dipolar and the contact interaction. So just contact interaction is R is 0, and then we crank up to some value which is RC, which is just the Unruh case. So you see these two spectra, this selection of spectra, Corley-Jacobson, standard, Unruh, generalized Corley-Jacobson, whatever, you can map it one-to-one essentially to a dipolar plus contact interaction BC. All these paradigms in cosmology. I mentioned here a couple of names. I hope I didn't omit too many. I mean, Robert Brandenberger was the major player initially in this kind of stuff. But also Renaud Parentani, and there's also some person present at this conference which contributed here, but not in this room, maybe. Okay, and Jens Niemeyer is not here also. Okay. Okay. And this Unruh flat band dispersion, we'll come back to that, it's very special. Okay. Now, as you might have expected, that's the point of my talk, of course, because of these Trans-Planckian modifications here, because of these Trans-Planckian modifications, so this is standard dispersion, just Lorentz invariance, this black thing. Because of these dispersions, you get a breaking of the duality invariance. So now what you see here is we concentrate on small k. This is a logarithm of k here. And the black line, and the black line is inflation. So just the usual scale invariance for small k. Actually, for inflation, it breaks for large k, but I don't show that here. So, and for the Lorentz invariance broken case, you see it deviates. It gets a blue tilt for below the Unruh spectrum, below the flat band dispersion, for small dipolar coupling. But remarkably, for just the critical case, just the flat band dispersion of Unruh, we get a red tilt. And remarkably, this is consistent with what is observed in the current cosmic microwave background. Of course, we have a lot of fine-tuning issues here, but it's a remarkable fact that we get exactly also a red tilt instead of a blue tilt to the Trans-Planckian violations of Lorentz invariance. Okay, so the result is, what is indistinguishable in the Lorentz invariant case? The Wants duality, which I refer to as Wants duality, the bounds and the inflation gets distinguishable by Trans-Planckian dispersion, and I've shown you a number of cases which are relevant here. They become distinguishable, these two scenarios. And this, I think, is a very good thing, because here we have a quantum simulator which is currently realizable in the lab. We have a quantum simulator of Trans-Planckian modifications of the scale invariance of the cosmological power spectrum, distinguishing the bounds and the inflationary case. For example, erbium and dysprosium, which have sizable magnetic dipole moments. As I said, this was on the archive 17 days ago. You can, of course, peruse further details if you like of this stuff. So thank you for your attention.
Do you have any quantity which is analog of the black hole mass?
Of the what?
Black hole mass. You know, if you want to simulate evaporating.
Well, you can in a quantum gas basically can do by, for example, laser potential, every distribution of density and velocity you like. But I mean, there's no Einstein equations in analog gravity so far. So there's no Schwarzschild would require, except you have a very weird equation of state, would require a velocity which is like 1/squared of r. If you want to talk about Schwarzschild geometry, this would be a rather exotic
this
case.
is like one-dimensional black hole. It's not really Schwarzschild black hole. I mean, as far as I understand.
You can do two-dimensional case, but it's experimentally way harder. Way harder.
But in the one-dimensional case, do you have analog of the mass, black hole mass? You know, what you expected.
You can
mass
evaporates,
so it goes down.
if you translate the surface gravity to a mass, of course, you can do every surface gravity you like. You can do the velocity gradient and density gradient, and then you can engineer every kind of mass you like. I mean, this is, but this is not the major concern in analog gravity at all, the analog of mass.
But that's the main thing, you know. You want to show that mass.
Yeah, but then you would need the Einstein equations, first of all.
Ah, okay.
I mean, to have a one-to-one mapping. You can do a mapping, but I mean, it's not one-to-one, of course.
I mean, it's one-dimensional. It's not realistic black hole, but at least.
Yeah, but I mean, ADS-CFT is also, and this is infinitely more realistic than ADS-CFT. ADS-CFT is a completely useless thing. This is useful.
Okay. Any other questions?
Thanks. I was just wanted to ask about that buildup, the oscillations in your density. I thought there was a sink and a source on opposite sides. Why are you getting this buildup exactly? Is this just because of the
Okay, we quench from initially non-interacting vacuum to a black hole configuration. So no interaction to the final configuration which we like. Because we want to have an initially well-defined quasi-particle vacuum. That's the purpose. Okay. And the source and sink, I mean, here's the source, here's the sink. Here you put them in, the BC particles, here you remove them.
Yeah.
Of course, this is of course far less than trivial to make source and sink with BC laser. You know, it's of course not trivial.
Okay.
I mean, but people have ideas on that.
Okay.
It's, I mean, so BC laser is not a trivial thing.
It's imperfections in the drain.
No. I mean, you mean the oscillations? The oscillations are...
Yeah. Are they just caused by the quench and then they'll drain?
Yeah. Okay. I mean, this is an observation. We analyze the spectrum. We analyze the spectrum of the system. And then we plot what is the lifetime.
Okay.
From the imaginary part. That's just a result in Bogolubov.
Okay. Thank you.
Okay, very well. Are there any other questions? One more.
So the one duality, I believe, that exists between massless fields really on the background.
Sorry, what are you talking about?
The Wand's duality, what you call, that really exists between the matter bounds and massless fields. In your setup, I thought the density perturbations or whatever you would do would have some mass term as well.
Sorry, I didn't get it.
So I believe the Wand's duality, what you are referring to, Wand's duality, that exists between matter bounds and the de Sitter kind of inflationary phase, A, and massless fields are required for that.
Yeah.
In your case, would your modes...
They are massless, of course, yeah.
Okay.
I mean, this is phonons. Of course they are massless.
How do you ensure that it is a matter bounds in your setting?
Well, I mean, the thing is, again, in the BC, you engineer the space-time background. You do it by the density and velocity perturbation. You don't have Einstein equations. You are God.
Okay, very well. If there are no more questions, we thank the speaker again. Now, I find myself in a very strange and funny and paradoxical situation. Being the chair of the last session, should think myself in home sense. We will skip
Just Eduardo told me to announce for the third time that the general meeting of the International Society for Relativistic Quantum Information will happen in this room starting at 4:45. So if you can make it, please do. It's an interesting society and being a part of it is useful sometimes. So yeah, thank you. Enjoy the coffee break.
Is this room going to remain unlocked?
Yeah.